All right, the second of our coordinate plane transformations lessons is about reflections. And so this time, again, we're talking about a rigid motion, but this time we're talking about reflecting over a line. That line could be the x-axis, could be the y-axis, could be some other vertical line or some other horizontal line. So if we're reflecting across the x-axis, what ends up happening is we move in a horizontal path, a vertical path across the x-axis. And so if I'm here at 3, 7, and I want to go across the x-axis, I'm traveling this vertical path, so my x-coordinate is not changing. So an x-axis reflection maintains the x value, and then the y value just changes to its opposite. The y-axis does the opposite thing. So if I'm going across the y-axis, now I'm traveling horizontally, and so that horizontal path is maintaining the y, and so I just change the sign of the x. So to keep this straight, if we're reflecting over x, we keep x. If we're reflecting over y, we keep y. Now if I go over the line x equals 6 in part C here, now that's a vertical line, so I'm traveling horizontally to the vertical line at 6. I need to count units. It's going to be 3 units from 3, 7 to the 6 line, and then it's going to be 3 units beyond. So what you can do is take the x coordinate that you have, determine the distance to the line that you're looking at, and then count again beyond that without even having to use a graph. We know that the y coordinate is going to stay the same because it's traveling horizontally across a vertical line. So that's where the 9, 7 comes from. Same concept with reflecting over y equals 4. Y equals 4 is 3 units below the point 3, 7. And so if I'm traveling to it and through it, it's going to be 3 units on the other side of the line, and that's where I'm at 3, 1. Okay, so in the diagram at the right here in exercise 2, point A has been reflected across line M, such that the image is shown as A prime, and points A and A prime are connected to form AA prime. That's a segment which intersects line M at point B. So we know 2 things to be true about any reflection in space like this. We know that the connector between the 2 points is always going to be perpendicular to the reflection line. And we also know that the original segment and the reflected segment will be equal because it's the same distance to the line as it is across from it. So we use these facts to figure out some things about the coordinate plane as well. So if we're reflecting over y equals x or y equals negative x, those are diagonal lines with slope 1 and slope negative 1. So anytime I reflect over y equals x, I'm reflecting over a line with slope 1, and the line, y equals negative x reflects over the slope negative 1. Okay? So going into exercise 4 on the next page, if we're trying to take the point A at negative 6, 2 and plot it along with those lines y equals x and y equals negative x, we can find the reflection across either of those diagonal lines by counting to and through the line. And then we'll talk about a rule for it in a minute. But if I want to go from negative 6, 2 to the line at y equals x, then I'm traveling in this direction, perpendicular, if you can follow my cursor, perpendicular from A to the line, and then the same distance across from the line. So what you can do, if it's a slope of 1, my reflection line is a slope of 1, I know that my perpendicular slope is going to be negative 1. So I can just count along a slope of negative 1 and see how many diagonal spaces, for lack of a better term, I have passed through. From point A to the line, looks like it's 4 diagonal spaces, so I can go 4 diagonal spaces exactly on the other side. And that's how I know that I've gone perpendicular. If I'm going across y equals negative x, now I need to go on a slope of positive 1 because I'm going across a line with slope negative 1. So that takes me up this way. Okay, and then using my results from above, what ended up happening is my coordinates switched, but the signs stayed with the numbers as they moved. So literally, y became x. If you reflect over y equals x, the x becomes y and the y becomes x. And it just switches the numbers. Nothing to do with signs. So this is different from rotations, where only one sign was changing at a time. This is changing both numbers and keeping the signs intact. Now if you go y equals negative x, what ended up happening there was the x and the y switched, but so do both of their signs. So the negative 6 moved to the other position and became positive 6. The positive 2 moved to the other position, became negative 2. So we're switching the numbers and we're switching the signs. So hopefully we can remember those 2 rules. All right, if negative 5, 3 is reflected across the line y equals x and then rotated 90 degrees counterclockwise about the origin, which would be the following image point. So we can do this with a graph. Negative 5, 3 is over here in quadrant 2. And go across the line y equals x, which is going, here's y equals x. I need to go at a negative 1 slope to do that. And that negative 1 slope would take me to here, right where my cursor is. And then I have to go across this way too. But I think an easier way to do it would be to switch the coordinates. We'd have 3, negative 5. Like, switch them with their signs. 3, negative 5. And then if I'm at 3, negative 5, I can then rotate one quadrant by switching the 3 and the 5 and checking the sign. So if I'm at 3, negative 5, I'm down here in quadrant 4, which means I'd be traveling to quadrant 1. So when the 3 and the 5 switch, they both become positive. And I'm at 5, 3. So the graph can help for sure, but so can just working off of the coordinates. All right, and then when we have this last example reflecting over a line that is not y equals x or vertical or horizontal, that's when it becomes a little bit trickier. So what we have to do is take the equation that we're reflecting over and determine its slope. Sometimes it's given to us, sometimes we have to write the equation from a line. But this one has a slope of positive 2, which tells me that my perpendicular path will be on a slope of negative 1/2. That's the first thing I want to do, is figure out what slope I'm traveling on, and then I can figure out how far to go. So in this case, when I go from r at a slope of negative 1/2, down 1 over 2, down 1 over 2, it takes me to the line at a coordinate. So that's nice, because then I can just count down 1 over 2 again twice, and I land on r prime. So that's the way that one works. If we had it not landing on a point, then we'd have to do some extra calculations to figure out where that point is. But in this case, and in most cases, you'll be able to change the slope to its perpendicular and travel along that path and find out where the prime is.